In order to figure out the shear force and bending moment diagram, the very first thing we have to do is to figure out the support reactions. Here we have a support of roller at point A and a pin at point B. Since rollers provide supports in the vertical direction, so we have a force acting vertically upward as AY, whereas spin provides supports in both horizontal and vertical direction. However, since all the loads are acting vertically downward, we will have the support reactions only going vertically upward as BY. Next, we can convert the distributive loading into a point load by multiplying 4 kilopounds per foot times 30 feet. That will give us 120 kilopounds. Next, we can apply the equilibrium equation as summation of forces acting along the y direction equals to 0 and add all the point loads. This gives us AY plus BY equals to 160. The second equilibrium equation can be written as summation of moment at point A equals to 0, which gives us the value of BY as 80 kilopounds. Plugging that information in equation 1 gives us the value of AY that is also coming at 80 kilopounds. Next, let's draw the free body diagrams. To draw the shear force diagram, we can utilize the loads acting on the beam. To start, we have a 20 kilopound load acting vertically downward that will cause a jump down from 0 to negative 20 on the shear force diagram. Next, we have a support reaction of 80 kilopound that will cause a jump up from negative 20 to 60 kilopounds. After that, we have a distributive loading acting vertically downward. The area under the distributive loading is coming around 120, meaning that from 60, 120 is subtracted. That makes our value on the shear force diagram to negative 60 at point B. Now, to figure out what will be the slope from point A to point B, we have to recall that we integrate the area. So we have a slope of 0 for a uniformly distributive loading. While we integrate that, it's converted into a linear relation. So from 60 to negative 60, we will have a linear profile. After that, we have a point load of 80 kilopounds that will cause a jump up. So from negative 60 plus 80, that will leave it to 20 kilopounds. Next, we have a point load acting at the very end of 20 kilopound, acting downward. That will cause a jump down from 20 to 0. Now, to draw the bending moment diagram, we can utilize the area under the shear force diagram. So to begin, we have a rectangular area of negative 20 times 15 that is equals to negative 300 kilopound feet. Since the slope is 0 for that region in the shear force diagram, on the moment diagram it will be linear. Next, I have a triangular zone and we can calculate the area of the triangular zone by half base into altitude that is coming around 450. So our moment diagram will jump up by adding 450 to negative 300. We get a value of 150. Next, we have to figure out the profile. Since we have a linear profile in the shear force diagram and integrating that, we will get a quadratic profile for the moment diagram. Similarly, calculating the area of the triangular zone next to it, it is coming negative 450. So our moment diagram will jump down from 150 to negative 300. The profile again will be quadratic since we have a linear profile on the shear force diagram. Finally, we have a rectangular area in the positive zone that is of 300. So our moment diagram will jump up to 0 and the profile will be linear as the slope of shear force diagram is equals to 0.